Forced oscillations and resonance. Forced oscillations and resonance. A person swings passively in a swing is an example of a free oscillation. If a kind friend pulls and pushes the swing periodically, we have forced or driven oscillations. There are two angular frequencies. One, the natural angular frequency omega of the system, if the system oscillates freely. Two, the angular frequency omega d of the external driving force. A forced oscillator oscillates at the angular frequency omega d of the driving force, and its displacement x at time t is given by x at time t equals xm cosine omega d t plus phi. So this is called the driving frequency, where xm is the amplitude of the oscillations. When omega d, the driving frequency, equal to natural frequency omega, then the resonance happens. A condition called resonance, at which the displacement amplitude xm of the oscillations is greatest. All mechanical structure have one or more natural frequencies, and if a structure is subjected to a strong external driving force that matches one of these frequencies, the resultant oscillation of the structure may rupture it. Look at this one. This is the amplitude, of the swing. This is the ratio of the driving force frequency and natural frequency. If they equal to 1, then they have a resonance. The amplitude is the maximum. These three layers is because of the resistance of external force be different. Okay?
This bowling ball pendulum will be used to demonstrate resonance. The pendulum swings with a natural frequency of about 1 swing every 2 seconds. We'll drive it by striking it with a rubber mallet. First, we'll drive the pendulum by striking it repeatedly at short intervals. Even after many blows, the pendulum isn't moving very far. But if we change the striking frequency to the natural frequency of the pendulum, the amplitude increases with each blow of the mallet.
This physical pendulum drives a rocker bar, which in turn drives 3 simple pendula hanging from the bar. The driving frequency can be changed by moving a weight on the physical pendulum. The weight is first adjusted so that the driving frequency is equal to the natural frequency of the longest pendulum. If the 3 pendula are initially stationary, only the longest pendulum responds strongly. The weight is now adjusted so that the driving frequency matches the frequency of the middle pendulum. Notice the strong response of the middle pendulum and the different phase lags between the driver pendulum and each of the 3 simple pendula.
This spring and weight hang from a driver whose frequency can be adjusted with this control. We'll increase the driving frequency slowly and watch the effect on the motion of the weight. At low frequencies, the mass moves very little. As the frequency increases, The amplitude of oscillation increases until the mass strikes the table. The weight is now lagging behind the driver, which is moving at the resonant frequency of the spring and weight. When the frequency is increased further, the amplitude of oscillation decreases.
We will demonstrate resonance by breaking a glass beaker with a sound wave. This beaker has a natural oscillation which can be produced by gently tapping its brim. We create a resonance by exposing the beaker to a sound wave of the same frequency. For this demonstration, we use a stable oscillator, a power amplifier, and a horn driver which can handle a large amount of power. The beaker is positioned on a foam rubber pedestal in front of the hole from which the sound emerges. The sound wave emitted by the vibrating beaker is picked up by the microphone to the left of the beaker and displayed on the oscilloscope. The oscilloscope is triggered by the signal from the oscillator, but displays the signal emitted by the beaker, so that both the amplitude increase and the phase shift can be observed as the frequency is tuned through resonance. The frequency of the oscillator has now been set to the natural frequency of the beaker. Using a stroboscope, the oscillations of the brim of the beaker can be viewed from above. Returning to a front view of the beaker, we now increase the amplitude of the sound wave until the oscillation of the beaker exceeds its elastic limit.
This pair of physical pendula have the same period. If we connect the pendula together with the light spring and set one in motion, the second pendulum also begins to move. Soon both pendula have nearly equal motions. Now the second pendulum has all the energy and the first pendulum has nearly stopped. The energy has now gone full cycle, with the first pendulum in full motion and the second at rest. If we connect the two pendula with the stiffer spring, the energy is exchanged much more quickly. If we change the period of one of the pendula by moving a weight, the energy no longer passes completely from one pendulum to the other.
Here is a device called a Wilberforce pendulum. It can oscillate in two ways: vertically and back and forth in torsional oscillation. After the pendulum is made to oscillate vertically, energy begins to transfer into torsional oscillation and the pendulum begins to twist. After a while, most of the energy of the pendulum is in torsional oscillations. The pendulum is barely moving in the vertical direction. Then energy begins to transfer back into vertical oscillations. Eventually, nearly all the energy is in the vertical oscillations, and the cycle begins again.
By the mid-20th century, the suspension bridge had come into its own. But in November 1940, something happened that would change these bridges forever. The Tacoma Narrows Bridge in Washington State opened in July 1940 and hit instant fame. Christened Galloping Gertie, this newly opened bridge began to oscillate uncontrollably.
It's making the hairs on the back of my neck stand up as I think about it, because you just don't want to go there. You know, it's a horrible, horrible thing.
On the 7th of November 1940, Galloping Gertie collapsed. For designers, nothing would ever be the same again. The collapse of the Tacoma Narrows was a wake-up call for suspension bridge designers. In pursuit of slenderness, they'd underestimated the power of wind. The mystery lay in the fact that Tacoma was designed to withstand 120-mile-an-hour winds. Yet the wind speed on the 7th of November 1940 was only 40 miles per hour. The key to unlock this mystery would be found in a phenomenon called natural frequency.
Natural frequency it would be something that's very familiar to anybody who likes music. It's the note that something makes. And if you pluck a guitar string or a violin string, you hear a note which has a particular frequency. And bridges are no different.
We've got three structures here. They've each got a different natural frequency. The natural frequency is the frequency it wants to vibrate at if you just give it a twang. And so we've got a really slow natural frequency here, got a really fast one, and we've got one in the middle.
In this test, the Tacoma Narrows natural frequency is most similar to the slow one. When winds hit a bridge, they create mini whirlwinds, called vortices. The problems start when these vortices have the same natural frequency as the bridge. This is called resonance.
If I now start to shape this support for these three bridges, if I do it really slowly, just give it a little motion, at the natural frequency of my big slow one, you can see that the big slow one really starts to respond, and we get massive amplification, and the other two are hardly doing anything. If I do it at intermediate sort of speed, the middle one goes wild and the other two stop. And if I go really fast, just a little one goes wild and the other two stop.
On that morning, with vortices created at the natural frequency of Galloping Gertie, it was only a matter of time before resonance caused the bridge's collapse. Tacoma terrified bridge engineers. Suddenly, wind was the enemy. They went back to the drawing board and discovered that the way to combat resonance was to bolt extra beams underneath the deck, called a stiffening truss. At vast expense, bridges around the world, including the Golden Gate, were retrofitted. It seemed the stiffening truss was the only way forward. That was until the late 1950s, when a young British designer came up with a new idea. And after countless awards, more than 40 years later, Bill Brown still plays down his role.
I think I was probably at the right place at the right time, in fact.
The magic of Bill's idea was to work with the wind rather than against it.
I didn't know that it would work aerodynamically. I knew it would work structurally, but not whether the aerodynamics would work.
Bill came up with the idea of reshaping the deck of the suspension bridge to make it aerodynamic. The wind is deflected around it, and the deck flies in the wind. Bill had just finished the Fourth Road Bridge and had won the commission to build a crossing over the River Severn. This would be the first bridge in the world to have this new deck. But first, he had to test it. 40 years later, Bill demonstrates what his wind tunnel tests showed. First up, he tests the Tacoma deck.
You can see the Tacoma Narrows section is twisting quite violently.
At just 40 miles per hour, the Tacoma deck cannot withstand the wind.
We now have mounted the 7 cross-section, and we're running this now at 150 miles an hour. As you can see, it is absolutely stable. This is because we have an aerodynamic section, the wind is flowing above and below it, streamlined, and the forces are low.
The 7 suspension bridge was opened in 1966 and would lead the way in modern bridges.
The magic is that it is streamlined, and therefore the wind forces are low, and there are very few vortices. So generally speaking, we don't need to add structural resistance to overcome the wind forces.
After the success of the 7, bridges around the world were built with aerodynamic decks, starting with the Humber. Resisting wind and earthquakes is a challenge, but there are other forces of nature out to get the suspension bridge. Over the years, engineers thought they understood the effect of people walking on a bridge, but they didn't.
How's you two? Break step!
Everybody knows about the Roman army having to break step when they go across bridges, and the reason for that is because they march very regularly. You have lots of people all putting their feet down at the same time, and if you get a bridge which happens to have a frequency which is close to that, the Romans must have found out 2,000 years ago that if they didn't break step, they would actually knock the bridges down.